So let's talk a little bit about significant digits and significant figures. This is something, the basic concept are pretty easy, but there's a few tricks and tips and things to worry about in the middle. So I'm just gonna talk about the basic idea, but it's in the book as well. So mostly I'll be going over problems and having you practice problems as well, ideally. And the idea is that significant figures, significant digits, express how certain measurements are. All but the last significant digit is exact. The last one is uncertain or estimated. Let's take for a minute looking at the volume as measured in a graduated cylinder. So we zoom in here, we can see that it's definitely more than 20. In fact, we can see quite clearly it's more than 21. But in between 21 and 22, it's not quite as clear. So I would say this would be something 21.6. So this would be three significant figures. So the 20 and the 1 are quite certain. There's no way it's anything else. But the 6 is an estimate at 6 plus or minus 0.1. 6 plus or minus 1 plus or minus 2, hard to say exactly. Now, sometimes when you're doing very precise experiments, you might come up with a more complete uncertainty. You might say, well, this is 21.6 plus or minus 0.2. But generally what is done in most calculations is to have a simpler way of representing the uncertainty, which is everything but the last digit is certain. And the last one, there's some uncertainty. And anything beyond that is just garbage. It's meaningless. And if you look at this meniscus here, it's 21. If I were to say is 21.654, is there any way I could figure that out? No. So anything beyond the significant figures is just garbage. And it's better for us if we acknowledge that we don't know a calculation any more than that. All calculations are somewhat uncertain. Things like Planck's constant, Avogadro's number, we only know out to 8 or 9 significant digits. Beyond that, it's just impossible for us to really figure out what is actually, what the number actually is. So it's better to embrace that uncertainty, but make sure we write that down in the calculation that we're doing. Okay, so let's start out with some questions. So I want you to think, and I'm gonna pause. Well, I won't pause that long. You can pause the recorder. And think about this. How many significant figures are there in 0.002400 grams? So pause for a second, think about it. All right, welcome back. The correct answer is 3. There's 3 significant figures here. The leading zeros put us in the right order of magnitude, but don't actually express the amount of uncertainty. It's these 3 numbers here. And the fact that the 0 is included is important. If we thought that this 4 was uncertain, we would have written it as 0.0024 and left it like that. But the fact that we included the 0 here meant that there's 3 significant figures. We know the answer out to that last one. That last one, maybe it's 0.00241, 0.00239. We don't know for sure, but we know it's something like that. We know that this is definite, that this number right here is definitely 4. Now, one thing you might want to do, it gets, it's generally better to write things like this in scientific notation. So I would probably write something like 2.40 times 10 to the minus 3 grams. And then it's even clearer that there are exactly 3 significant figures. Okay. Next question. How many significant figures are there in 6.3803 times 10 to the minus 3 grams? And again, I'll pause for just a second, or I'll let you pause it so you can think. All right, so we're back. Now, remember, the significant figures is not the number of digits after the decimal place. It's the total number of digits that express the accuracy in the number. And so in this case, there's 5 here. 1, 2, 3, 4, 5. Those are the 5 significant digits. This is a placeholder so that for exactly where the decimal point goes. It doesn't say how many significant digits there are. One thing that can be a trick every now and then, if you were to see a number like 640000, and you were to ask how many significant figures are there, it's a little ambiguous because if you're going to write 640,000, then you really need to have, you need to show that it's that big. But usually zeros that are trailing there are zeros that you mean to have. That's a little ambiguous. What I would always do in numbers like this is to write them in scientific notation so it's absolutely clear. If you were to see this, you can think, you can come up with rules for which of the zeros are significant or not. But if you read something like this in a book, you read that number, you're never going to know which rules they were following exactly. So it's really better to always write numbers like this in scientific notation. I could write this as 6.4 times 10. Let's see, 1, 2, 3, 4, 5 times 10 to the fifth, and then it would be absolutely unambiguous what the number was. Or there's two significant figures, or 6.400 times 10 to the fifth. There we go. It's very clear. There's 4 significant figures. So that's something to think about with positive exponents as well. Next problem, let's get a little more applied. This is an engineering class after all, so something you're always going to be dealing with is some sort of waste disposal. So a chemical waste storage drum at a local company originally weighed 73.6 kilograms when full. After being stored accidentally without a cover overnight on the loading dock, this will happen, somebody does it, it weighed 68.2 kilograms the next morning. If 1 kilogram is 2.205 pounds, how many pounds of volatile chemical waste in the correct significant figures should be reported as being accidentally released into the environment? Let's pause here. I'll let you think about that for a second. Pause the video. All right, we're back. So let's just see how much is missing. So we have 73.6 divided by 68.2 kilograms. So we get 5.4 kilograms. And so we could say, well, there's two significant figures, but we need to report it in pounds because stupid processes have been around forever. So we'll need to report it in pounds. That'll be, so there's 2 significant figures in this multiplication. 2.205 pounds per 1 kilogram. So we get 11.907 pounds. 11.907 pounds. And so looking at this, we have only 2 significant figures in the initial answer, in the initial subtraction. That's the lowest number we have. So in this multiplication, the conversion, in this case, we're giving it to 4 significant figures. There's only 2 significant figures, so the answer is going to be 12 pounds. So 12 pounds, D, will be the answer that we report what's gone. So this is what we've gone through here. There's plenty more practice problems in the book.